We are the Dendritic Identification Team, and we're Group 19. I'm Evan Lenz. I'm an in-person student.
I'm Quentin Thompson, and I am an in-person student.
I'm Daniel Van Loon, and I'm an online student.
Kyle Helbert, and I'm an in-person student.
I'm Luis Placencia. I'm an online student.
Dendritic Identifier, or DI formation. You can think of the DI as nature's fingerprint. When we form these structures, random instabilities in the material create chaotic, fractal-like patterns. Because those instabilities are never exactly the same twice, every DI ends up with a unique pattern. We create this pattern using a stamping process. A small amount of liquid is dispensed between two plates, then compressed and separated. That simple action generates the branching, dendritic structure you see in these images. This process is easy to scale, it can be done in large quantities and on many different kinds of surfaces. We can also tune parameters like stamp size, the applied force, and the viscosity of the liquid to change how the pattern looks. On top of that, we mix in mica flakes. These flakes reflect light differently depending on what viewing angle they're at, so every DI ends up with its own sparkling constellation. DI use and authentication. Because each DI pattern is unique, we can use it as a physical authentication method, basically a built-in security tag. The nice thing is that DIs are scalable, so they can be made as larger labels or shrunk down to millimeter-sized features on components such as ICs. For authentication, the flakes and branches inside the DI create a set of key points, distinct spots and junctions in the pattern, like the ones highlighted in the images. When we want to verify an item, we measure its key points and compare them to the stored references. If they match, the item is considered authentic. Overall, DIs are distinctive, localizable, repeatable, and robust, which makes them very promising for anti-counterfeiting and secure identification.
Potential customers. Who would pay for this? The big end customers are organizations that absolutely cannot tolerate counterfeit parts. That would include entities such as Department of Defense, aerospace companies, IT hardware manufacturers, and Homeland Security. These are organizations where a fake microchip or missile component can cost lives or compromise national security. Closer and more common to us is a supply chain are as wholesalers, luxury good makers, and even everyday consumers who want to know their product is real. Imagine scanning a tag on an iPhone or a handbag, or even produce at the grocery store, and with your phone, you can instantly get a verified message. Because the dendritic identifier itself is unclonable without the original master, everyone from the factory to the end user can trust the verification system. This is a process that the image on the right shows us. From application to verification, we can see how the process would work to verify the product. Project scope. Our senior design project was to build a complete working system around this idea. We needed a device that was low cost and user friendly, but still accurate enough to read these tiny dendritic identifiers. The camera required manual zoom, focus, and aperture adjustment capabilities to give the user quick, easy adjustment options that could be completed as the system was being used. The verification system needed to take high magnification photos, control lights at different angles and heights so that the constellations of flakes showed up clearly. It also needed to run computer vision code to extract and compare key points and store the original reference data so it could be checked later. This would eventually mean creating a storage server to save encrypted images for the comparison process.
For our final build, we wanted to supplement design decisions by including ray tracing models of the ideal setup. We used an open source ray tracing program from Demo to model it. On the bottom right is the model for the flakes, being perfect mirrors at various orientations. The top row of images show an example of light sources at 65, 40, and 30 millimeters respectively to match our setup. The bottom row depicts how a light source situated around the camera will reflect off the flakes, and how changing the camera height can increase the angle of acceptance for reflections. The final build is entirely 3D printed and was designed using Fusion 360. This allowed for us to have a concrete process for manufacturing that was repeatable and precise. We started with small and simple parts, which allowed us to experiment with print tolerances and press fitting. Once designs were finalized, we moved towards a final build which was modular, sturdy, and accomplished the goals outlined in the project scope. As for the implementation, the lighting assembly at the top includes the light ring, the LED ring, which situates around the camera, and the individual lighting sources which chain together on the height adjustable light ring. The general form of the structure is also depicted on the right with the main building blocks. The base with press-fit legs, including height adjustment pegs, the printed ring for holding the individual light sources, and the camera mount, which attaches seamlessly to the base. We saw great improvements in part quality as we dialed in the tolerances, and the result is a final build which met our design goals.
To support testing, we developed the software interface that captures, stores, and authenticates the images. The GUI was built in custom Kinter, which gave us a clean layout and modular structure. Connects directly to the camera and controller, allowing full control of brightness, color, and angle of illumination. We had a debug logging configuration file so that the same code can adapt to different hardware setups without actually rewriting the code itself. The main goal of the software was to make testing fast and repeatable. We can capture multiple reference angles, adjust exposure live, send each image to the comparison algorithm automatically. So it bridges our physical setup with the image matching. The original path for comparison focuses entirely on the reflections from the microflakes rather than each dendrite pattern. First, we do point extraction, detecting the bright spots or stars in both the test and reference images. Next, we use astro-align to estimate the rotation, translation, and scale between those constellations. If astro-align struggles to converge, it falls back to a ransack routine, which iteratively refines the transformation. After alignment, we do geometric verification by checking three metrics: the number of inliers, the root mean square error, and the coverage, which measures how widely the matches are spread across the pattern. If at least 3 points align and RMSE is below about 12 pixels, we consider it a valid match. This method was simple and fast for single reference comparisons, but it was sensitive to lighting differences and rotation. That sensitivity led to false positives and false negatives, which motivated the development of a more robust method. Final software pipeline moves from imaging to normalization, tissue isolation, sparkle extraction, and finally geometric verification. First, we normalize rotation and geometry using Aruco markers. This removes rotation, translation, scale, and perspective differences across captures. Then we normalize lighting by sampling the interior of the markers and applying a photometric gain correction. We then isolate the dendritic identifier region using the known marker geometry and refine that region using a grab cut segmentation mask. Sparkle extraction uses posterization, local peak detection, connected components, and edge erosion. An adaptive retry loop adjusts the thresholds if too few or too many sparkles are detected. For verification, we apply mutual nearest neighbor matching. Because normalization has already aligned everything, the correct transform between the reference and the test is the identity. Ransack is used not to compute a transform, but to verify that all match points are consistent with the identity transform, since normalization has already removed the rotation, translation, and scale. We then apply 4 decision metrics: RMSE to check how closely the matched sparkles align in pixel space, coverage ensures the matches are evenly distributed across the entire DI region, inlier fraction measures how many of the matches agree with identity during ransack, and minimum pair count confirms that there are enough reliable matches to be statistically meaningful. With all 4 conditions satisfied, the DI is considered a match. The advantages: matching uses lightweight numerical operations, so it runs quickly even on modest hardware. The Aruco-based normalization removes rotation, translation, scale, and perspective variance, making the sparkle geometry stable across captures. The marker-based photometric normalization compensates for LED brightness variations and exposure changes. Some of the limitations are it does require Aruco markers. Without them, it can't normalize orientation or isolate the DI. The markers fail or sparkle extraction becomes unreliable, the matching cannot proceed. DI region extraction depends on accurate marker geometry. Misprints or misalignment reduce reliability.
This first test shows two different images taken of the same dendrite at the same angle. So even in this case, we still have outliers, which is caused by factors such as a difference in lighting or just the software picking up different reflections. And in this case, due to the low root mean square error value and the high coverage percentage, it was given a pass, meaning that the dendrite was properly identified. In this next case, we took the image of the same dendrite, but taken at an angle of 90 degrees. And in this case, we actually had less outliers, but because of that angle difference, the root mean square error is slightly higher, but it was given a pass because the coverage is still high and the root mean square error is low enough to show that it is the same dendrite. And in this final case, we compared a dendrite with an image taken of a different dendrite. And in this case, as you can see, the coverage is much lower and the root mean square error is much higher. And on the left, you can see that the coverage is lower because points were picked up in a region in that middle graph that were not picked up on the left graph of that different dendrite, causing the coverage to be lower, as well as the different point positions resulting in the higher root mean square error, meaning that the ultimate result is a fail. And that is it.